Okay, so now we're looking at this free response question. This one's kind of cool because it's blending together our momentum and also our simple harmonic motion ideas. So what we're saying is, shown below, we have a 0.2 kilogram mass is sliding on a horizontal frictionless air track with a speed of 3 meters per second when it instantaneously hits and sticks to a 1.3 kilogram mass initially at rest on the track. The 1.3 kilogram mass is connected to one end of a massless spring, which has a spring constant of 100 newtons per meter. The other end of the spring is fixed. So we want to determine the following for the 0.2 kilogram mass immediately before the impact. So we want to know its momentum and its kinetic energy. And that's not too bad. This is kind of just us plugging and chugging. We know that our equation for momentum is P equals mass times velocity. We see that we have a mass of 0.2 and a velocity of 3. So our momentum is going to be 0.6 kilogram meters per second. Then kinetic energy. Again, we know our equation for this, kind of pluggy and chuggy. 1/2 mv squared, 1/2. We said the mass is 0.2, the velocity is 3, so 3 squared. And we get 9 times 0.2 times 0.5. I'm going to use my calculator for that. We get 0.9 joules. Okay, now we have a collision. So we want to determine the following for the combined mass immediately after the impact. So we do kind of two things for this. We could come in here and actually, no, we can do one thing because we don't know the speed. So what we can say is, well, for the linear momentum, we know it has to be conserved. Our system starts with a linear momentum of 0.6 kilogram meters per second, which means that our final system has to have 0.6 kilogram meters per second as its momentum. The momentum hasn't changed. Momentum is conserved, and we don't have any outside forces acting on it immediately after the collision. So, but then what we have to do is we have to use our kinetic energy, 0.2 plus 1.3 for the mass. We have to use our momentum equation to figure out the velocity. So what we can say is, well, we have a collision. Oops. So we have kind of before the collision, and then we have after the collision. So before, the only thing that's moving is going to be our m1. And we said the total momentum before is going to be 0.6, which means the total momentum after has to be 0.6. And if we're kind of thinking about what's happening, these two objects, they're sticking together, which means they have this kind of, we can picture them combined mass. We can picture combining the mass as one heavier object, one object that has a mass of 1.5, the 0.2 plus the 1.3. And they're moving with some sort of common velocity. So what we can say is our final momentum is equal to the final mass times the common velocity. So we're going to have 0.6 divided by 1.5. So our final velocity is going to be 0.4 meters per second. And then we can use that to figure out the kinetic energy. We can say 1/2, the mass is 1.5. The velocity we just solved for is 0.4. 0.5 times 1.5 times 0.4 squared is going to be 0.12 joules. And let's just make sure that that makes sense. Yeah, so as long as the energy didn't go up, we're good to go. If the energy went up, that would be kind of weird because where would that extra energy come from? But the fact that this energy is dissipated, that totally checks out. That's something that would happen in this situation. Maybe we lost to the spring, who knows? Or just kind of heat when these objects stuck together. Who knows? But that energy definitely, it's not going to be greater than afterwards. All right, now what we want to do is determine the amplitude of the harmonic motion and determine the period. All right, so this one is kind of tricky, but now we're kind of pivoting over to energy, this idea of energy. And if we kind of picture our two situations, we have the two objects are all in kinetic energy over here. Here we have the situation where we have these two objects moving with the maximum velocity. And then we get to a situation, we get to a point in our motion where this spring is fully compressed. So this full compression, and our object is stopped. So yeah, we're kind of sitting at this normal position, and then we have this movement, and then we get to a spot where our two objects, they come to rest because they're stopping. and then they're turning around. So they kind of come to this maximum compression, and then eventually we'll get moving again and kind of flow in that simple harmonic motion. But we just kind of care about this change from these two situations, from maybe situation A to situation B. So at A, we're thinking about what kind of energy we have. Say, well, that looks like all kinetic energy. All of our energy is tied up in this energy of motion. We're moving, our spring's not stretched yet, and yeah, we have potential energy, but let's just say that we're at the same height throughout all this, so it doesn't really matter. And then we're saying, okay, well, that's situation A. At situation B, we have no movement because we're kind of at this maximum turning point where our object has to come to rest for a brief moment to turn around. Yes, we have spring potential. Again, we're not going to worry about gravitational. So our kinetic energy is all converted into the spring potential energy. So if we can figure out the potential energy, the kinetic energy, we can figure out the potential energy. And we did figure out the potential, or the kinetic energy. We said the kinetic energy is 0.12 joules. So our total kinetic energy at the beginning equals our total spring potential energy at the end. So we have 0.12 joules is equal to the spring potential energy. And we have an equation for spring potential energy where this 1/2 kx squared. And we said before that k is equal to 100 newtons per meter. So when we solve this out, we have 0.12, that's supposed to be a 2, 0.12 equals 50 times x squared, 0.12 divided by 50, and then I'll square root that. Right, so say x is equal to 0.0489 meters. And the amplitude, again, is just kind of defined as the maximum compression, the maximum displacement. So this is the spot where we have the maximum displacement, the maximum displacement. And then the final little thing, determine the period of the harmonic motion. So we know for a spring, we have this equation that says the period is equal to 2 pi square root of m over k. I think, yes. Yeah, let's roll with that and then we'll check. So Ts is equal to 2 pi. We know that the total mass that's oscillating is 1.5 kilograms. We know that the spring constant is 100. So let's just kind of plug in and check in. 1.5 divided by 100 times 2 pi. So Ts is equal to 0.769 seconds. All right, and let me just really quickly, if I don't come back, it means that this equation's right. I just get it mixed up. I don't remember if it's k over m. Yeah, that should be good.